How would you go about modifying the trajectory of an asteroid?
Good question. We need to build a ship that will be a deep space mission ship that can apply large amounts of thrust to it. A 27 million ton asteroid is not something we can just easily manhandle. My plan is we go into space well in advance. If we launch a mission in October of 2027, that gets us docking with Apophis in March of 2028. And at that point, when we start pushing hard, and pushing hard is a relative term, we push hard on this big giant asteroid using ISP 5000 ion thrusters, magnetoplasma dynamic or Vasimar thrusters will do the job. They can handle 5,000 ISPs or even higher. Then we can push on it hard enough to accelerate it by, would you believe, 6/1 billionths of a G. And you do that long enough, well, it turns out to be 1 centimeter per second per month of acceleration. So we thrust for a month and it's going a whole centimeter per second faster or slower, slower in this case, which is a tiny change. If we do that for 10 months, building the speed up to 10 centimeters per second, and then you coast for another 3, that total difference delays the asteroid by those 200 seconds so that the Earth is 6,000 kilometers farther away, and all the other things, all the big changes are handled by the Earth's gravity and later by the Moon's gravity. So we just do this little bit, and assuming our 5,000 ISP rocket thrusters takes 55 tons of fuel to do that. So it's doable. We can handle 55 tons of fuel.
So the astronauts will actually land on the asteroid. They will set the thrusters, and then depart and allow.
I don't think they'll depart.
You don't think they'll depart?
I think this is a little deep space mission. I think they are going to land on the asteroid, and their rocket is going to be thrusting continuously, pretty much for the next 10
so
months.
They're going to be hooked up to the asteroid.
They're going to dock to it. You don't really land.
Like a huge sticky boom or something like that. Something like
they're going to be
John
pushing.
Goff's Altius space machines.
I actually think we'll run kilometer-long cables around it and tie it down. So you've got to hold on to it somehow.
27 metric ton, what does that translate into in terms of size?
It's 27 million tons.
I'm sorry,
it's
27
million metric tons. 27 million metric tons. It's 270 meters across. At least we think it's 270 meters across, and we think it masses 27 million tons. So it's not too big. It's several times bigger than a football field, like almost 3 of them. And it's probably a big potato-shaped pile of gravel, or rubble piles are what most of these asteroids are, so it's not going to be one big chunk we can drive a stake into or hold on to. It probably means we'll have to use something like ropes around it to hold on to it.
Now, at the point where it comes back around the Moon and heads back towards the Earth, I can see that some people might think, well, if you're going to draw it into Earth orbit, perhaps there's a chance of it, increased chance of it crashing into the Earth.
Yeah, and that is well-founded. The approach we use for this needs to be looked at very closely by independent teams, intense oversight to make sure it's done right. Because you don't want to take that chance. You don't want the thing to hit the Earth, because it's big enough that if it hits the Earth, then it'll destroy something about the size of Connecticut. It's not going to be a global catastrophe, but it'll certainly make a very bad day for whoever's underneath it. A little bit worse if it hits the ocean out and it's probably going to be in the Pacific. In 2036, if we don't do anything and it actually hits, then it'll zip by the Pacific 1,000 miles or so off of San Diego. And that would be bad, because you get 60-meter high tsunamis coming across LA and San Diego, and there will be trillions of dollars of damage and tens of millions of lives potentially lost. We'll have much warning. I mean, we could evacuate, but do people really believe you and really evacuate in time? I don't know. No, it's dangerous, and we know we need to do it right. One of the reasons I'd like for us to do it, and by us I mean the United States, NASA, our group, is because if we don't do it, someone else probably will. There's too much money involved. I think we can invest something of the order of $30 billion to generate something of the order of $200 billion a year of revenue. Those are big numbers. And if we don't, someone else probably will. It could be the Chinese, could be India, it could be contracted out by the Saudis or Dubai or United Arab Emirates. They have the money, and they may not have the resources except for money, but money buys a lot of resources. So I think we should do it to make sure it's done right, safely and right. A lot of people are worried that having a new moon, and it would be a new moon around the Earth, would impact the tides or change things, and it's way too small for that. If the moon is 3,000 kilometers across, this is less than 300 meters across. So there is a factor of 10,000 in diameter, which you cube that for the mass difference, it's not measurable. We cannot measure any impact this thing would have on the Earth, on the moon, on anything. It's just too small.
How bright would it be in the night sky?
You could see it. It would, but it wouldn't be brighter than any of the other stars. It's not. It's unless it got really close.
So it wouldn't be as bright as the ISS?
It's probably going to be comparable. When on its close approach, it'll be possibly brighter than the ISS. It's farther away, but it's bigger. But part of that depends upon how bright it actually is. You see, we don't know its albedo. We know how bright it appears, and we know how far away it is. But in reality, it could be a different kind of asteroid than we think. It could be brighter and therefore smaller. It could be darker and therefore larger than we think. One of the real instructive things is there's an asteroid called YU-55 that we used to think, a little over a year ago, we thought this thing was 140 meters across and weighed 4 million tons. Well, it was imaged by radar last April, a year ago April. And when we looked at it with radar, the radar said, no, this thing's 400 meters across. And the calculations say, now that it's 400 meters across, it doesn't weigh 4 million tons, it weighs 87 million tons. So we were off by a factor of 22 in how big this thing was. I hope that's not the case with Apophis, because I don't see how we can pump enough fuel up there to modify its orbit if it's 22 times as big. On the other hand, if it's half as big, that's better. It's easier for us to modify its orbit.